this live stream link, I'm going to send to you, Richard Janoski, and you can share that with anybody that needs that. I think we got an email earlier today requesting access to that. So I think we're good to go. We can switch back to sharing our screen, and we'll run through today's presentation, which is about grease compatibility studies. And the question is, can your next grease change cause issues? Is really what I want to address and get into today, because the answer to that is yes. When we say, can your next grease change cause issues, we're talking about if you're going to be switching products. So what I'm going to talk about is discuss why mixing greases in general is a bad idea. What kind of problems can it create? What kind of issues does it bring up? And I'm just going to check quickly. I heard in my headset that my microphone was lost. Can you still hear me okay? And looking for confirmation that I'm still broadcasting into the session. Okay, very good. And then why using compatibility charts is an even worse idea than mixing the greases in the first place. And I'll talk about all the pitfalls around using these compatibility charts, which I'm afraid are still in widespread use. People are making maintenance decisions based off of that today, and it's a big problem. So what should I do if I can't avoid the mixing? Because everybody says just don't mix greases. It sounds so simple, but it often isn't. What happens when the product that you're using is no longer manufactured? What happens when you have a corporate-wide transition from one supplier to the next? How do you deal with that? So sometimes you can't avoid that mixing. And I want to talk about what's really in ASTM D6185 and why there is a working group that's looking at changing some of the things around that particular standard. That's the standard around evaluating compatibility of binary mixtures of greases. The question comes up, how can I work greases like they are worked in the real world? And I'll compare that to that ASTM standard and the methods that are there, and talk about that, as well as demonstrating our test stand here and talk about interpreting results. So what happens when we mix greases? What can happen to that? Well, the grease can get runny, the grease can get hard, it can leak out of the machine that we put the grease into. We can see that the grease fails to lubricate, fails to perform its function. Sometimes after this happens, we mix greases and we find something that's hard as a rock in there. We are unable to pump the grease. Ultimately, it can lead to machine failure. And I dropped this image in here, one that I took on a job site of a critical air handling unit fan. This is how we found that bearing. Gentleman said, I think that bearing rusted out. But what we found in there with what was remaining of that bearing was some grease residue, which we were able to sample, analyze, and evaluate. And we found evidence of a polyurea thickened grease and a lithium complex thickened grease had been mixed together in this bearing. The result was that the mixture had softened, the oil was released from the thickener, ran down the front of the equipment housing, leaving behind just the thickener, which is not adequate to lubricate. And the result is an oxidative wear mechanism that looks like something like rust. Red oxides, black oxides. Bottom line is machine failure of a critical component. So what do people turn to? Well, a lot of times it'll be to these compatibility charts. And I'm going to explain why I think that's a bad idea. Now, here's one compatibility chart. It's published in a well-known magazine, and it's this typical format where you have families of thickeners. You've got aluminum complex and barium and calcium 12 hydroxy and complex, and so on down the line. And as you look across, you will see that match up to the different types, and it'll either give you that they are compatible, that they're borderline compatible, whatever that means, and incompatible. Now, borderline compatible, I guess what really matters is this going to negatively impact the operation of my machine or present or future maintenance activities? And that's ultimately what should be determining whether something is considered compatible or not. But again, this is a very loose definition. And one thing I'll point out is that this particular chart, if I choose to select it, disagrees with this chart. And this chart disagrees with this chart. So you find out that these charts do not agree. I wrote an article for Machinery Lubrication Magazine where I researched 17 different grease compatibility charts like this. And I found that a few of them appeared to be the same chart in a different format because they match perfectly, but most of them had variations from chart to chart. Very few of these charts reference any testing that was used to create them. So if you're going to put your valuable assets on the line based off of this chart, wouldn't you want to know who came up with the chart? What data they used to produce this chart? Too often I think people just say, hey, I found a chart that says they're compatible, we're good to go, let's change out the greases. And unfortunately, that's a recipe for disaster. So we don't typically find what testing was performed to create them or when they were created. So the world of grease is not static by any means. Grease is constantly being formulated. New products come onto the market. Old products go off of the market. These charts may have been around for 5 years, 10 years, 15 years. Okay, so face that direction. So what's the microphone then, Richard? Do you know what it is? The phone is the microphone? Okay. Yeah, so let's try to help this along here and get maybe some consistency in audio. And I apologize for that. I've got a headset on, but it doesn't appear to be working today. So, another thing about these charts that we should consider is that they do not reference the testing. They do not account for the base oil differences. These charts are only based off of the thickener and the thickener family. In fact, within these families, you can have variation. You can have, you say it says here calcium complex. Well, that could be 20 or 30 different formulations. You can choose a number of different acids to mate up with that calcium to create that calcium complex. And so it's lumping them all together and pretending as if they're all having equal compatibilities with other products. It doesn't take into account any of the additive differences either. So there's a lot that leaves to be desired here, and putting your faith in these compatibility charts is a very bad idea that's fraught with danger. So why do we run a compatibility study? Well, we said that the default is just don't mix the greases, but we don't necessarily have that as an option all the time. So if we have to take one product and introduce it to another product and it can't be avoided, or if it's too late, we made a mistake, we already mixed and we want to know what's going to happen next, maybe it's a critical component, and we want to know, should we shut it down and dig this incompatible mixture out or potentially incompatible mixture out? It's when we're getting all the old grease out is impossible or impractical. So that's the other thing. If you can't avoid mixing, then clean out all the old grease. Easier said than done. Grease is designed to stay in place. That's why we're using grease, because we've got an application, because we need that lubricant to stay in place. So it's very difficult to get it out short of complete disassembly of a machine's parts and then cleaning them thoroughly, sometimes even with solvents and things like that. To do this while the machine is still in service can be very, very difficult, very impractical, and possibly very costly. So if we can make a determination of compatibility and know whether this is even necessary, we might be able to save a lot of money and improve the reliability and even the life of our component in the process. See, even if greases are made the same base oil and the thickener type, they might be incompatible. So even things that are self-referenced on that chart, calcium complex, they might be the same. They look like they're the same thing, but they may be incompatible. So we can evaluate these grease mixtures to prevent these issues if we have a supply or formulation change. So maybe a grease isn't available anymore, or there's been some kind of reformulation, or maybe we just go to a new supplier and we just don't have access to the old grease. If the greases are incompatible, mixing them during use could lead to significant changes in the flow characteristics and shear behavior which could result in inadequate lubrication. And that's why we would run the compatibility study to understand what might happen and what is the risk. So the compatibility study allows for evaluation of mixtures without risk to equipment or affecting uptime. We can use the data that we produce by running these tests to support the ability to mix greases either slowly, if it seems like that's an okay mixture, if it passes this kind of compatibility test, or to know whether maintenance needs to be scheduled to change out those greases and possibly disassemble that equipment to achieve that complete changeover. And then we just use this information to assess the risks and the costs of the alternatives that we might have before us. So what about this D6185? And so people looking to evaluate grease compatibility often end up at this standard. It might go to a laboratory and ask for a quote for D6185, a compatibility study. And there is a primary test protocol for that, and that primary testing uses three different mixtures to evaluate grease, 1090, 50/50, and another. It actually also allows for 25/75 and 75/25 mixture. So we're looking at the different mixture ratios that the grease might experience during a transition, let's say, where we start to add a small amount of the new grease. It starts to bleed that down. Eventually we get somewhere in the middle, and then towards the end we just have a small amount of the original grease left over. The tests that we run with these prepared mixtures are the dropping point, the shear stability test, and the storage stability test. Now, these tests involve using a grease worker, and the grease worker does a back and forth kind of disruption of the thickener for a set number of strokes. And for this test, we end up doing 10,000 strokes to the grease. If all the mixtures pass this primary testing, or an application requires some specific evaluation that's not found there, the method does say secondary compatibility tests can be used for further evaluation. But in my experience, end users rarely ask for or even realize that this is meant to be just the first step in a compatibility study. And instead, they say, hey, I've got the results of the compatibility study. These products are compatible. Full speed ahead. Let's start mixing these greases. Another thing I want to point out about these tests, the dropping point test, the shear stability, and storage stability, if you look at these methods on their own, which involve cone penetration and the higher temperature dropping point, those methods do state that these are meant to be static tests and have no bearing or no influence on the performance of an in-service grease. Therefore, the compatibility study itself is basing properties of grease which don't predict its dynamic performance in the machine. But when we think about compatibility, aren't we thinking about the machine, right? When I mix this grease with that grease, is that going to work? Is it going to move around that bearing? Is it, as it gets sheared and moved around, is it going to perform as it should? But these tests don't look at those dynamic conditions. What about the working of the mixtures? Well, the ASTM D6185 does this 10,000 double strokes in a grease worker. Sounds like a lot. And I think if you're the person doing that, you could get worn out. It's kind of tiring. It seems like a lot of working of that grease into a mixture and giving it some semblance of working conditions as these greases are brought together. Now, what we have found is that we historically have not always seen that the performance predicted by D6185 matches up with what happens in the field. In other words, you could have two greases that were tested by that primary test or initial test, if you will, from 6185, and they pass that as being compatible, and then we see something else happen in the field. We might see the grease get soft, we might see oil bleed from that because of that mixture, or we might see it later harden up, and as a result, that's really not the outcome that we're looking for. So some time back, we worked to create a simulation that's closer to what happens in the field. And I'm standing in front of that test stand today talking to you. This test stand involves these bearings that you see here. And so these are a kind of the style of bearing that you would see not in a pillow block housing like this, but more like you might see an electric motor bearing, which has a flat profile for that. And we've got two of these special pillow block bearings on each shaft, and we have 4 shafts in this test stand, and then some heat lamps are available for that process as well. This is a split housing style, and so you've got that easy access where we can just put that over top of that bearing, run that, and then remove it and gain access to the grease that has been worked in this setting. And so part of this is that we need to get good access to it. And, in a minute, I'll show you here how we do that and how we transition from one grease to the next. You might be able to see here we've got some white grease and a blue grease that are mixed together in there. And that's giving us, this is the result of a test there where we've mixed these 2 different greases together. And then we can sample after that working. Now, the setup of this is that these are 9-ball deep groove ball bearings. They operate at 1795 RPM, and based off of the ball pass frequency on the outer race, we can look at that ball pass as a mixing event. And if we take that 72 hours at 1795 RPM, 9 balls, 3.6 balls passing that point per revolution of the shaft, that gives us in 72 hours 28 million mixing events. So 10,000 versus 28 million. Now, is that just overkill? Is that over the top? Well, the other way to look at this is to say if the grease worker is to simulate the mixing events, let's say in an electric motor, that 10,000 events is equivalent to about 93 seconds of working in a typical electric motor bearing. So the question is, from a simulation standpoint, from a confidence standpoint, are you going to be happy if that mixture lasts and is compatible for 93 seconds of operation? I'd say not. But you wouldn't be happy with it for 72 hours either. But it does give us enough time to see some of the physical changes that we can observe in grease and measure them very precisely to gain some insight into the compatibility of this mixture. So we have this greater degree of working. We do the same kind of baseline ratios that you see in the 6185 outlined there. We kind of verify the suitability of the mixture, that we've actually gotten a good mixture of these 2 greases by looking at FTIR and RDE, looking at the additives, looking at the thickener and the base oil to make sure that we've created a very good mixture for this grease prior to packing it into the bearing. When we're done, this is when we would take our samples. We would use the grease thief, which I've demonstrated multiple times here. We could use the pillow block sampling kit and take the grease, and we're really going to be reaching down inside to the bearing here to get that grease that's been in there and working that whole time. Use that grease for our analysis. And then we're also going to do some things like look at the formulation differences. Have we been diluting additives by having 2 different products here? What is the function of the 2 products? And we look at those formulations and compare them. So here's some of the comparison that would go into the report, like even before we do this testing. And that includes comparing the NLGI grades. Okay, you've got a lithium 12 hydroxystearate thickened grease and a lithium complex. A lot of the charts will say that they are compatible. Okay, but compatibility is one thing. Compatible function is another, right? Is this grease that we're going to replace here, is it going to do the same sort of thing? Does it have the same kind of properties? And here you can see on these 2 products, while the thickener might be compatible, there are different NLGI grades, which will have some effect on the result of the mixture. And then we can look at the penetration values and then also look at the viscosity of the base oil. This one has a fairly wide range that it specifies for its base oil viscosity, but it may or may not be critical depending on your operation. The one below that is looking at 2 different greases there, a polyurea and an anhydrous calcium grease, fairly close in the work penetration values. The viscosity does have some differences there. And again, you'd have to look at that and say, does this new grease have a viscosity that would be suitable after being mixed with this other grease, and how would that change the viscosity, and how would that affect its film forming capabilities, typically elastohydrodynamic films that we're looking for in rolling element bearings. So to interpret the results, we want to pass the mixtures that would have a response, typically that are between the two baseline greases, and I'll show you that in a moment. If you have changes outside of this, much higher values or lower values, it kind of implies that you just don't have an averaging of these two greases that were fairly close to begin with. Something else has happened physically, chemically in this mixture that has changed the properties to a completely different value. And so I'll show you some of those examples. Here's some results. Now on the left, you see the table at the top. This is our rheological data. And when we think about incompatibility of greases, we think a lot about, hey, those thickeners get too hard or too soft or something like that, just in general terms. Well, rheology is going to give us that ability to see how those flow-related properties, the consistency, how it flows, how it shears, and so forth, how they're going to change in response to being mixed together. And so on the left, we've got this table that looks in a couple different areas here. It's got the G prime value, which we thought of as a storage modulus, sometimes related to kind of the pumpability of the grease, how well it'll stay in place, how firm it is, that sort of thing. And we compare that. We also look at the yield stress. And the yield stress could be related to other changes in properties, such as how it shears down, how this mixture down will shear down relative to how the individual greases would behave, the likelihood of it to bleed. If that's going to change, you might see that in that value. And then the third property that's measured is recoverable compliance. And think about this in terms of, when you've got grease packed around a bearing and it starts to spin, the motion of that bearing pushes grease out of the way. A well-designed grease has the ability to slump back in to contact with the bearing. Now, some greases, as they age or stressed or what have you, lose that ability. And if you've worked in maintenance, you may have seen this, where you take apart an older piece of equipment and you can see that bearing or that gear that moves in the middle, and you have this void around it. You've got a wall of grease around it. We call that channeling or tunneling. And we can gain some insights into changes in the likelihood of that grease to channel or tunnel by looking at significant changes in its recoverable compliance. So that's how we look at these different values. The one on the left, the chart at the bottom is our G prime values, and you can see the light blue is a pretty significant difference in the G prime to begin with between these two products. But we do create with the dark blue bar there what the numerical average would be, and see if the mixture kind of averages and falls into that. And instead, it's a much, much lower value than either of the greases were. So it's kind of generally can be thought about as a softening type of process by mixing these two greases together. That's compared to the other mixture that's shown on the right, a different mixture of greases, and the G prime values start out to be fairly close. And the mixture, after it's been worked for 72 hours and so forth, comes out and the value is right about where we expect it to be. So just based off of the rheological properties there, much better performance when we think about its compatibility between the two products. Again, looking at the yield stress in this next table, same product on the left where we looked at the G prime before. Now we're looking at the yield stress. Okay, you can see some different values there and the numerical average, yet the mixture behaves much differently. It's a much lower yield stress, down at or even lower than the lower yield stress value for the two greases that were mixed, versus, again, this grease on the right that performed much better in the testing. Even though the yield stress was quite different, the numerical average is very close to what we saw when we mixed these two greases together. So they're behaving as two separate performing greases that have been mixed together, and they're kind of averaging out their performance to be somewhere in the middle, versus showing some difference in how they behave, which is explained by something happening at the molecular level, at the bonding level, physical, chemical, whatever it happens to be between these two products, that tells us that the one on the left is not compatible. So before I open it up to questions, I want to stop my sharing here and switch my screen to the video, and that will allow me to see what I'm showing you from our test stand. All right. So I've got one of the setups here, and you can kind of see the grease mixed in here and so forth. What we need to do with the setup is to be able to transition from one test to the next. And we have this set up with these kind of Lovejoy style couplings so that we can come right in here and lift this shaft out of the housing, kind of gently take it off, take the coupling off, and now we have it out. You can see I've got some positioning spacers here at this end on this bearing, and we would remove obviously that one on the end, be able to take this to another location where we can kind of carefully clean the grease off of this, and use solvent or whatever is necessary to get that all out, get it dry, get back to the bare bearing that we started with, and be ready for another test. So that's part of the design here that allows us to do that. And since we don't want to get into a big job of having to do realignment and so forth each time, we built it with the bases in alignment, can place the bearings right back into the same location with the spacers that you see here, and then go back and put our covers on after we've cleaned up that bearing. So that's our setup for testing. We do have then a Zerk fitting here, but generally we're not using that for this test. We're just setting it up, putting that in place, and then hand packing it, running it for that period of time, taking it apart and doing the test. So at this point, I want to see if there's been any questions raised. Okay. So Mindy says, do you make the mixture blends prior to adding them to the simulator, or is the simulator designed to help mix up the various blends? Great question. We do mix it up before we put it in the simulator, and then we do testing with that mixture to make sure that it is a good homogeneous mixture by taking a sample and looking at the distribution of the additives through RDE testing or spectral testing, and then FTIR. So we're looking at the thickener, the base oil, the additives, and making sure that we see this numerical average that will tell us we've got a good mixture there. We can compare that whether it's a 1090 or 50/50, and we're really keying in on the high contrast either elements or parts of the FTIR that'll show us that we've got an average going on and we've got a good mixture prior to loading it into this unit. So that's a good question. Yeah, I would not want to rely just on this to mix it up because it's really not optimized for that. That manual mixing process really helps. And we've been doing some ILS preparations, and we've been using some different kinds of mixers, speed mixers and things like that, which really enhance that process, really help you know that you have a good mixture together before you go to do your subsequent testing. Now, you can make the argument that that's less of a simulation than what happens in the real world, right? The real world would be you fill this up 100% with one grease and then you slowly start to add the other. But there's so many variables there, it's very difficult to kind of get it truly simulated to real world. So we work on making sure that the mixtures that we're evaluating, we know what they were at the start, so it's going to be replicable. And I saw maybe some other questions. Oh, there's more about sound and quality, and hopefully, Chuck, we got things straightened out for you that you were able to kind of come along and hear what I had to say after a while. Any other questions? Okay, here's Chuck. Have you compared? Let's see, a new question. Let's see if I can find this one. Have you compared results using the 72-hour bearing test to the 10,000 worker in the rheology test? It's a good question, Chuck, because that might be what we would need or what would help to kind of know the difference, how much of an improvement this is. We just don't happen to have that worker available here. So since it's not readily available, we're not doing it. But I like the idea, and it's something that we can do and kind of compare them, and then that would help folks understand what the difference is between the approaches. I just like to look at kind of the numbers behind it and say, it's just not a lot of working really when we think about how much these greases really do get worked in a bearing, in a housing, and that sort of thing. But I like that idea. I think we like to do that. And now Mindy's maybe offering it, so maybe we'll send some greases out to her, get them mixed, get them back, do our thing here, start to put them side by side and see what the differences are. I like that idea. Maybe we'll work together with SGS to get some results for folks on that. Thank you, Mindy. Anything else? Anybody else? Yeah, Chuck's got a good point. It might be that this kind of elaborate setup is not needed if we can see the same kind of things happening, and then maybe those folks who just have the grease worker could use that, and maybe some expanded dynamic testing like the rheometer and some of these other tests, as well as, and I think this is really important too, and is often overlooked. If people only do that primary testing on D6185, even if they expand it to say rheology and they get a dynamic test in there, it isn't necessarily also looking at the other important considerations, which is what are the formulation differences? How does this line up to the application and so forth? And I think, for asset owners who are like putting their trust in us as laboratories to help figure this out, I think we're doing them a disservice if we don't consider that and bring that up as part of the evaluation and just say, hey, we ran these couple little tests and this is the numbers, right? It's more than that. It's about having confidence that the results will give the direction that someone needs to make the right decision. And it's hard to do that in a vacuum if you don't think about how are these formulations different, how are the additives different, how does that translate into possible success, regardless of whether the dropping point or something else is not substantially changed by the mixture. Okay, well, I want to thank everybody for joining us here today. We're going to take next week off because next week I'm going to be teaching laboratory lubricant analyst training, LLA level 1, and I'm going to be doing that throughout the week next week. This is our first training class that we're doing live and in person since a year ago today. So that's exciting. We've got a great facility here. We've got good spacing and separation and a lot of other precautions that we have in place. So we like that. We're also going to be broadcasting. So if you would be interested in participating in that class, Laboratory Lubricant Analyst Level 1 certification training, go to our website, go to the training. You could do that remotely. We're going to be broadcasting that live using this Digital Samba platform. And if you'd like to sign up for that, you could still do that for next week. But because of that, we're going to skip a week and come back the week afterwards and pick up our next Greasy Thursday with which, Richard, do you have that in front of you? What our topic's going to be in 2 weeks? So I think you said it was for Ruler, and we're going to have a guest speaker maybe, or some others participating. But yeah, I think that sounds great, and I'd encourage people putting that on your schedule. Skip a week and come back and see us again in 2 weeks. And if you got the time and it interests you, look at our website for the Laboratory Lubricant Analyst training next week, available through MRG Labs. So thanks again for joining us, and we'll see you again in 2 weeks.